Hello, everyone. So I'm going to talk about the other side with respect to the previous talk, namely a constructive side. So how can we build better and better systems? How can we provide more and more security guarantees while having a practical system? And that's very challenging, but we've been able to make one step at a time. And I'm going to tell you about two steps in this direction, Myler and Verena. And this is joint work with my wonderful collaborators, some of which are here as well. So the problem we're looking at is the fact that web server could be compromised and confidential data can leak. For example, you have the web server stored in a cloud and a hacker breaks in and steals a snapshot of the data. Myler and Verena aim to improve confidentiality and integrity in the face of compromised web servers. So to understand these systems, I like to think about the following security spectrum. On the left side, you have today's systems that process data in decrypted form. So an attacker breaking into the server is going to see all the data, so everything leaks. A first big step towards more security is to be encrypt with end-to-end encryption-sensitive fields. For example, the developer can say that the medical history in this medical app is sensitive, and encrypting it with end-to-end encryption will make a big step forward. This is particularly relevant to passive attackers that just get a snapshot of the data and can see that the sensitive fields are encrypted. But then we have active attacks that can compromise the server in arbitrary ways. And an important step towards security for these attackers is to make sure that the attacker cannot compromise the client-side code, because client-side code has access to decrypted data. And in the web setting, this is not so trivial because the client-side code comes from the server who's compromised. Another important aspect is to make sure an active attacker does not tamper with key distribution because keys can decrypt. Another property going forward towards more security is to not allow any tampering from the attacker. No tampering with data, no tampering with computation and results of computation. Then yet another step is to hide metadata. So not just the sensitive fields, but the information about them, such as who has access to what. Then we also have access patterns. How do we hide access patterns during computation as well, during search as well? And this is very difficult to do today in a practical way because we know that ORM-based techniques are quite heavy and quite slow. And finally, there's this miscellany of topics that also leak, and we would like to hide them. And those are, what operations are you running on the data? What's the runtime? When are you running a query? The data size and the structure. And these are very hard to hide as well because many times they involve worst-case padding, and that can bring a lot of performance overheads. But if we can hide all of these, then we can give very strong security. I'm not saying perfect because there's always usability concerns and assumptions we make, but you can give very, very strong security. So unfortunately today, we don't know how to build practical systems with this target security. We have a bunch of relevant tools in theory, such as ORM, Garble RAM, and FHE, but they are too slow for practical systems. Building a practical system is much more challenging, and we've been able to make steps at a time. Now, each step contributes a conceptual property on top of what existed, even if it doesn't give you perfect security. So I've done a lot of work along this spectrum, and let me tell you today about two systems, Myler and Verena. Myler provides end-to-end encryption for annotated fields. And against the attacker that compromises everything, it provides two guarantees. One, that the attacker cannot tamper with the client-side code. And the second, that the attacker cannot lie during key lookup. Then comes Verena, which tries to prevent the attacker from tampering with the data and the query results. So the attacker cannot give you crap. Okay? Even if the web server is compromised, it's going to give you, as results, the correct results. And actually, fresh off the press, we have a new system, Opaque, that we're preparing the camera ready for, that actually hides all metadata and hides access patterns, including during computation. Opaque is based on oblivious algorithms combined with hardware enclaves, and if you're interested in that, then I can come next year and tell you about it. But Opaque focuses on data analytics, so not the web setting, and there's a bunch of other challenges to address in the web setting, so there's a bunch of to-do left here. Although we expect that some of the techniques from Opaque will apply to the web setting because Opaque supports rich functionality. And for the last category, it's a big question mark. It's really not clear how to hide that information in an efficient way. Okay, so let me tell you now about Mylar and Verena. So Mylar is a web framework that protects sensitive data fields with end-to-end encryption. The developers specify which are sensitive fields, for example, private message in a chat, and the browser encrypts these fields and gives the encrypted data to the server. So for example, if Alice has encrypted sensitive data, the browser encrypts it, if it's a sensitive field that was marked by the developer, and sends it encrypted to the web server. Okay, and the web server is only going to see these fields in encrypted form. It's never going to get the decryption key from the browsers. And when Alice accesses the data, the browser decrypts it for Alice. So from Alice's perspective, everything is seamless. Prior work has already proposed encryption in the web setting. However, they were far from sufficient to use in real web apps for a few reasons. First, we show that the common web framework, such as Django and Ruby on Rails, is not compatible with encryption, and we propose a different architecture. Second, in these systems, the data sharing was burdensome. Users had to do manual key distribution many times. Third, there are active attacks on client-side source code and key distribution that can lead to significant data leakage. And finally, there's no support for efficient server-side search. So Mylar addressed these challenges, and in this talk I can only tell you at a high level about two of them. How do you prevent active attacks on key distribution, and how do you add support for search server-side? All right, so the API in Mylar is that the developer says which fields are sensitive, and Mylar is going to encrypt them. Mylar does not protect anything else. The developer defines the access control, so who has access to those encrypted fields, using a principal graph. So the principal graph looks like this. Let's say in a chat application, the developer specified that Alice, Bob, Eve, chat work, and chat party are principals. And the edges denote access. Okay, so Alice and Bob has access to the chat work and no one else. Each of these principals has a key, actually multiple keys, but think of a key. And these keys are actually stored at the server, encrypted. They're encrypted with keychains, which I won't tell you how they work, but the property they give you is that only the users that have access to in the principal graph can actually decrypt the key. So only Alice and Bob can get access to the green key. And now the information inside each chat is encrypted with the key for the chat. However, there can be an active attack on key distribution when a user looks up a key. So consider that Bob wants to write some text in the chat work, okay? So he needs to fetch the green key from the server. So he tells the server, okay, give me the green key, give me the key for the chat work. But the server is malicious, might give him the purple key. And as a result of that, Bob might encrypt the data in a way that it can see it, and that's not what he intended to. To protect against this attack, Mylar certifies keys. Okay? For example, the green key certified by Alice. So she produces a digital signature saying this green key corresponds to the chat work, okay, by Alice. And Mylar supports arbitrarily long certificate paths similar to X509. Okay, the problem though is that, okay, now when Bob checks, fetches the key, he can check the digital signatures on the key, but how does Bob's Mylar client know that he's supposed to check the key against Alice's signature as opposed to someone else's signature? For example, Eve can also create a chat work. Only Bob knows that he wants the chat work with Alice. Okay, so Bob has to tell this to Mylar. And for this reason, in Mylar, principals have human meaningful names. The developer is supposed to display the certification path for every relevant principal that the user might give data to. For example, in this case, we have 3 available chat rooms. One is work created by Alice. That's the certification path for work. Work created by Eve. Anyone can create a chat with the name work, especially if they're malicious. And party by Eve. Okay? And the user is going to choose the work by Alice. That's where he wants to input his data. He wants to talk to Alice. Then Myler can check that the key he gets from the server is certified by Alice. And he won't be tricked into accepting the purple key. Okay? So to prevent against this active attack, we made an explicit design decision. That is that Myler does not hide the name of the principals and does not hide what principals have access to what. Okay? We want any user coming in and wanting to give access to a principal, to some data, to know who that principal is, who gets to see it, who certifies it. Okay. So the second part about Myler I want to tell you about is search. So Myler provides searchable encryption as a separate package from the main Myler system. And it works by, if the developer specifies a field as searchable, then Myler is going to enable searchable encryption for that one. And we have an access control function that's very important here, allow search, that controls who can see search queries. Okay, so let me tell you how Myler does search. First, let's consider using standard searchable encryption. You tokenize every chat into keywords, and then when Bob wants to search for, let's say, SSN, he has to give a token for each one of those chats with each one of those keys. And then using regular searchable encryption, the server sees that there's a match or that there's no match. And we build, and the problem is that, as already Paul mentioned, the client has to generate tokens for each one of these chats, which could be burdensome, so it would be really much nicer to generate only one token. And that's basically what Myler contributes here. So Myler gives the server a delta, which allows the server to convert, so an encryption of SSN, into an encryption with the 2 different keys. And then it's just regular searchable encryption from there on. Okay? And because Myler builds on searchable encryption, it has the same properties, the same leakage patterns as searchable encryption, namely that the server is going to know that there was a first match there, and then there was no match, and there were no matches. Okay? So the server is going to see the matching pattern. Okay, so to mitigate the amount of information that's seen in a multi-user setting, we designed specifically the allow search function. So we designed it for the following attack, which we described in the Myler paper. The attacker compromises the server. The attacker creates a principal called attacker with the key. So he has the key for the principal. It gives access to Bob. Bob generates a delta automatically. And then when Bob searches for SSN, the attacker can convert that into an encryption under the red key. That's what the delta enables you to do. And then can mount a dictionary attack. Okay, just because the attacker has the red key, he can mount a dictionary attack and figure out that SSN is what's encrypted. And then the attacker is going to see that, oh, that matches in other documents as well, just by the searchable encryption functionality. So because we were aware of this attack, we designed the allow search function specifically for it. The point is that a user should not automatically give the delta to anyone giving them access. The delta should only be given to trustworthy principals. Okay? So the developer must call allow search on trustworthy principals. Sometimes it has to ask the user, do you trust this principal, this person, to know your search queries? Are you fine if they know your search queries? Or other times, the developer can just figure out from the application logic, for example, the boss can have the allow search. Okay? But the point is that the attacker should not get the delta. Okay? So the allow search makes sure that only trustworthy principals get access to the queries. So because of this, the attacker, okay, and the other thing is that the attacker cannot fake that he's boss or doctor because Myler certifies principals as we just described. Okay, so because of allow search, the attacker is not going to get delta, and he's not going to know the query, what was searched. All right. So going back to our security spectrum, here's where malware lies. And it's natural right now to discuss the previous paper that Paul presented. The very first point that was not so clear in the presentation is that malware does not claim to provide full confidentiality, perfect security. Okay, the paper has a bunch of places where it clearly says attacks it does not protect against that are out of scope. Okay, now looking at the 3 leakage scenarios that Grubbs et al. Evaluate, we find that the first 2 are out of scope, and the third, we believe it does not work if you use malware correctly. Now, I want to say that even if things are out of scope, they're still useful, right? Because in my security spectrum, right, we want to get all the way there. We want to have all these properties. So by all means, even out of scope attacks are useful, but we just have to be aware that they're out of scope and that they don't actually affect what the system gives you. So concretely, if we have a medical application, let's say malware encrypts the medical history of each patient, okay? So it protects the contents of the medical history. Malware does not protect that Dr. Alice can see Bob's medical history, okay? That's this explicit design decision that we made, that it will be known who has access to what, for certifying principles, as we discussed. Second, malware does not protect the fact that Dr. Alice has access to Bob's medical history, okay? And protecting that is really hard to do efficiently. ORAN-based techniques are very slow, so most practical systems don't protect such leakage, okay? What malware gives you is the fact that the content of the medical history is encrypted. Regarding the attack on search, this is the same attack that we described in our malware paper, the one I just showed you. It has the same 7 technical steps. And we designed allow search specifically to stop this attack. Okay? So it is the same attack we were aware of in 2014, and we designed allow search to prevent it. And if you want more details, step by step, please take a look at the malware's website. All right, so going back to our security spectrum, this is where the attacks of Grubbs et al. Are. They don't affect the 2 steps of security that malware gives you. They're still very useful because we want to get all the way there. So we want to understand what we have left to do. Speaking of left to do, let me make another step forward in this spectrum and tell you about Verena. Verena ensures that an active server attacker cannot tamper with data, computation, code, or keys. And it provides 2 benefits. First, it gives you confidentiality against a wider class of active attacks than malware did. And Verena was designed for malware. It has the same architecture, so it was designed with malware in mind. For example, if the attacker, if the server removes one of the users from a ban list, then it might be the case that later some user gives access to that banned user because they didn't know he was banned and leak, okay? So it's important to take care of tampering for confidentiality as well. And then, of course, for end-to-end integrity, where you want your users to get back correct data results. The threat model in Verena is that the web servers can be fully compromised, okay? Really fully compromised. And here's what Verena gives you. So let's say you have a pacemaker application where the user's pacemaker sends heart rate samples to the web server. And you have a doctor that analyzes this to give a diagnosis. For example, the doctor wants to know the average heart rate for Alice in a timestamp interval. The doctor is going to receive back a result from the web server along with a proof, okay? So in Verena, the web server is going to prove that the result is correct. And what do I mean by correct? Well, if the doctor checks this proof and the proof was correct, then the doctor is guaranteed that the data was only changed by Alice, so the heart rates come from her, so right access control, that the data was complete, no sample was removed, that it was fresh, latest, and that the average was computed correctly. There's been a bunch of other work that try to provide these properties, but they're not applicable to the web setting. First, because it didn't deal with multiple users, and there you have access control, you have lack of coordination, and it's not fit for the web setting because the web setting is stateless. So let me tell you a very high-level flavor of how Verena achieves these properties in the web setting. First, if we consider that the web server can be fully compromised and that users do not coordinate with each other, the problem is that there's an impossibility result saying that you can't actually give freshness. The attacker can fork the users. Namely, after a while, the doctor is no longer going to see Alice's updates. So you can, in order to bypass this impossibility result, one makes some trust assumption. For this, we introduce a hash server, and the trust assumption is that it does not collude with the server. Okay, so at most one of the two servers can be malicious. Okay, either one can be malicious, including the hash server, but at most one. And our hash server is very simple. It's mostly a key value store for hashes, and it has a small TCB. And what we are going to use it for at the high level is to store the latest hashes of the data so that when the users get data back, they can check them against those hashes and make sure they're fresh. In Verena, the developer has to specify the integrity policy, and it does so using our integrity API that, interestingly, it's attached to queries, not data. In fact, in Verena, we don't really care what happens to the data of the server. It can be changed, it can be deleted, as long as the server answers correctly to all read queries. Every query in Verena runs in a trust context. This denotes the members, the users, that are the only ones allowed to affect the result of the query. For example, if you select the average heart rate for patient Alice, then the trust context is the patient Alice, okay? Only she, her device can change the result of this query. If you want to select the list of patients, then only the admins can affect the result of the list of patients. Okay, so if this is our integrity API at a very high level, how do we enforce it? And a very important building block for us is authenticated data structures. These are basically search trees sorted by the range field, in this case timestamp. The leaves also have the values, like heart rate, the values we want to aggregate. And then each internal node has a partial aggregate that is the sum of the values in the subtree, the sum or some other function. Let's go with the sum for now. Okay, so for example, in this subtree, 150 is the sum of 80 and 70. And then there's a Merkle tree that's built on top of this, okay? And if the client has the root of the Merkle tree, then the client can efficiently verify a proof from the server, in which the server proves that the interval of interest of the user has that aggregate, okay? Using the properties of the Merkle hash tree. So this is all work that existed, and we're going to use it. Verena is going to compile the integrity policy into a forest of ADS trees that are linked with each other. The root of each ADS tree will be stored at the hash server to ensure freshness. So let's consider a complicated query, and let's see how Verena handles it. We want the average rate, so we're joining two tables, patient lists and patients. Okay, from the patients list, we want the patients with age greater than 70, and then for each one of them, we want their average heart rate in a time interval. So what Verena does is the server goes through all this trust context to assemble a proof of correctness. First, it uses the trust context admins to assemble a proof that this list of patients that it's returning is complete and contains all the patients with age over 70. Then it goes into the trust context for each patient to compute the average heart rate for a time interval and prove that that one is correct. Okay? So using this forest of trees at the high level, Verena can give you the properties we talked about. And there's so much more I haven't covered, so please take a look at the papers if you're interested in that. One point I want to make is that both Myler and Verena have modest performance overhead, so they're practical systems. So in conclusion, Myler and Verena make significant steps towards providing security in the face of compromised servers. We open sourced Mylar, and we plan to open source Opaque as well. Hopefully, it will help the community. Building real-world crypto-based systems is very challenging, but we can make one step at a time. And each step removes a whole class of attackers, even if it does not give you perfect security. And I hope I showed you that there's a bunch of really cool work left to do, and hopefully this session will get you interested in working on it. So thank you.
So we have time for questions.
Hi there. On one of your slides in the middle of the Mylar portion of this, you suggested that users could select which principles they wish to trust. After decades in this field, I have been unable to find a deployed system in which this works. Users are not capable of making security decisions, so far as I can tell. And if you leave security decisions to users, systems fail. And when I was young and naive, I actually believed in constructing systems on the principle that you could let users make decisions like this, and I have long since been disabused by bitter experience.
Yeah, so I agree with you that a lot of users don't make the right decisions, and I agree that
almost none. I mean, the number you can basically guarantee that perhaps a fraction of % of users will make the correct decision.
And I also agree that it's not necessarily easy. It sounds somewhat inherent because we need to know what the user wants, who do they want to give access to, and moreover, their thinking is that they will use this kind of system for critical applications where hopefully they could be more educated and be more incentivized. I agree with you that it's hard to make these decisions correctly, but I don't know of any other better technique because the user has to convey to us what principle they mean. At the same time, I think there's really important to do more work on this, on the usability studies. Maybe they don't select the path. Maybe you make the sequence of pages be so natural that they go to the right place. So that would be usability work. Great point, though.
Let me just intervene for a moment. We're actually already 8 minutes late for our excellent sandwiches. So if you could keep the questions succinct and also try to keep the answers short, that would be much appreciated. Thank you.
So I have a short philosophical question. You're saying this is better than nothing because you protect against some attacks, even if not all. But it's also more dangerous than nothing because if people have false trust that the system is good, they're going to put all their vulnerable information and use it with extra trust. So I just wanted to hear what you think about that.
So I think that the user should not have this false feeling. I think they should be informed, right? We're giving you end-to-end encryption for fields you mark sensitive. We don't hide anything else. They should be informed, right?
Building a comprehensive secure system is a Sisyphic and hard task.
Yes.
And what you call users, call them highly trained veteran security experts, because it's not, sorry about my voice, it's not like you don't have a, so if you have some primitive in cryptography that is like, zero knowledge proof, if I add it to an input and I verify it, in any context I can do it. It's a very robust and you can put it in, you don't need to be an expert. If you use a system that is like a Swiss cheese, it covers certainly but has holes, you need really experts to know where is the hole and where is not the hole and how the system is going. And you need to monitor it all the time, where you violate the cheese and gets into the hole. It's very complicated, but in certain, it's not robust in the sense. Security is not going to be maintained. And I think don't use users, use experts.
Yeah, so I agree that users have to be, they have to be careful here. The one thing I want to say is that this applies to many other systems we have today, right? So whenever you have end-to-end encryption, they need to understand that they don't protect access patterns or metadata, okay? So this is not necessarily specific to Mylar. Pretty much every practical system has some things it offers and some it does not. And it's really a mistake to think that it gives you all the security guarantees there, because there's always going to be things outside of the threat model. And the second point I want to make is that we absolutely should work on usability of these systems, thinking how to make them usable, how to make users not mistake. And that requires some work that's complementary to Mylar. Right now, we're trying to even figure out how can you technically do this. Before Mylar, there wasn't end-to-end encryption embedded with web apps at all.
Sure.
I have a question about the searchability. You don't produce a reverse index on the server. Instead, we're encrypting each term with some randomness, and that's why these attacks that reveal the order of keywords work. What's the difficulty with reverse indexing?
No, so you can totally actually randomize the order for each document. You don't have to keep them in document order. And we did actually have a reverse index implementation as well, and that reverse index is done based on encryption, so in some sense they're randomized already, so it would not reveal the order. Yeah.
Okay, well actually we're out of time, so let's thank Raluca and all the other speakers. Thank you.